All right. 1 minute, Christoph. All right. Thank you all for coming. We have a pretty dense schedule for this Splinter session, focusing on wavelength calibration techniques, technologies, and processes. I'm thrilled to have a diverse set of speakers. We're going to kick things off with Christoph Lovis, who's going to tell us about the espresso thorium to FP bootstrapping. Go ahead, Christoph.
Okay. Hello, everyone. Can you hear me okay? And can you see my slides as well?
Yes, you're good.
Okay, so let me go through this Thorium Fabry-Perot wavelength calibration scheme that we are implementing with Espresso. So I'm going to describe the main steps briefly. So we start with a reference thorium line list that we take from Redman et al. But we make a selection. We select only strong unblended lines that we can fit without being perturbed by neighboring lines. And we try to pick lines with low pressure sensitivity, which are defined as lines with a low energy upper state. So this is something we have not investigated much, but it is in principle it is known that the higher up you go on the upper state energy level, the more sensitive to pressure shifts you may be. And so we try to limit that. So this is the first thing. Then, well, these lines, they have to cover the whole wavelength range. We need at least one line per spectral order. But this is completely different from the previous situation with thorium argon only wavelength calibration, where you needed thousands of faint and mostly blended lines to cover the spectral range with thorium only. So we no longer need that, and that's a big booster, a big advantage of this thorium FP wavelength calibration. It also avoids issues with the super strong argon lines that are saturating large portions of the spectrum in the red orders of Espresso. So it is enough to have just one valid line in per spectral order to carry out this procedure. So of course, in compensation, it is the FP peaks that have to cover all the spectral orders with sufficient flux, because we are going to need them to fit the wavelength solutions everywhere. So then we define a calibration sequence. In Espresso, it is made of 3 exposures: FP-FP, thorium FP, and FP thorium, that I'm going to detail afterwards. And so the idea here is, because these are 3 different exposures, we can bring the thorium and FP spectra for each fiber to the same reference frame by correcting for drifts between these different exposures. And so the scheme, the general scheme is the following. You have these 3 calibration exposures: FP-FP, thorium FP, FP thorium. The first FP-FP exposure should be a high flux exposure, because you need to have and to be able to fit FP peaks everywhere on the spectrum. Then the thorium FP exposure is used really to perform the wavelength calibration of fiber A. And for that, we are going to use the thorium spectrum and the FP spectrum from the previous exposure. And to do that, we compute the drift using fiber B to really correct, to correct for the drift between these 2 exposures. And we do the same with the FP thorium, so as to be also able to wavelength calibrate fiber B in the same way. And of course, all this is for calibration. And then when you do a science observation with a target on fiber A and FP on fiber B, you're also going to compute the drift with respect to the thorium FP frame, and you are also able to correct this drift here. So this is the general scheme that we are using. So the steps are the following. We first measure the pixel position of all thorium lines and FP peaks in the spectrum. Then we assign an absolute mode number to all the FP peaks by numbering them across the whole spectrum. Then it's the main step. We can get an independent measurement of the FP spacing from each thorium line. We just need the known thorium line wavelength, the mode number of the neighboring FP peaks, and the pixel positions of the thorium and FP lines around the thorium line under consideration. So essentially, this is no magic. It's just using the echelon equations. The echelon equations for lambda m and delta lambda m. Also the assumption, we need an assumption of a locally linear wavelength solution. So when I say locally is really around each thorium line and including the neighboring FP peaks. And so you mix all that and you can get an equation that will give you the FP spacing for each thorium line. And then when we have all these measurements, we fit a Savitsky-Golay kernel to the measured FP spacing versus wavelength, which will naturally take into account the FP chromatic drifts. So in practice, this looks like this. What you see here is the FP cavity length in angstrom as a function of wavelength. And so each dot represents a measurement derived from a different thorium line and the Fabry-Perot lines around it. So you see it's a smooth function. So we fit a Savitsky-Golay kernel on this, and then we can look at the residuals. This is what is shown here. These are the residuals around this Savitsky-Golay fit. It's expressed in meter per second now. And so you see on the large scales, it's pretty flat. But of course, we are not photon noise limited here. We are systematics limited. Clearly, you see the error bars. Well, most of the time, the error bars are much smaller than the dot size, actually. So you see that the scatter here is fully dominated by systematics that we probably don't fully understand, which are probably related to PSF effects, also to maybe still some blends on the thorium lines, and also other effects that we can maybe discuss later. But anyway, these are the residuals from a random espresso calibration frame that I considered here. And then we are almost done. We determined the final FP wavelength using the fitted FP spacing and the echelon equation that directly provides lambda m as a function of d and m. The final step is simply to fit polynomial wavelength solutions to the FP lines in all spectral orders. So nothing really fancy here. We have many FP lines in each spectral orders, hundreds of lines. So a simple polynomial fit is good enough to, well, you just need to adopt a polynomial degree that is sufficient to take away all the large scale residuals. But otherwise that's it. And so just to show you the impact on espresso. So this is a tau ceti. I think I showed this plot already yesterday. So in green, you see the data before we implemented this the Savitsky-Golay fitting. Before we were just fitting a single achromatic offset to the FP spacing. We had a fixed FP spacing relation, and we were only fitting an achromatic offset because we didn't know to what extent there could be a chromatic component. But you can see that after a few years of data taking, clearly things were really degrading, getting really ugly. And so after implementing this chromatic fit of the FP spacing, we recover a stable tau ceti, which is good, of course. And finally, I show again what Tobias showed this morning. So Tobias made a similar verification, just taking two different epochs of espresso, 2018 versus 2021, so roughly 2 or 3 years apart. And you can see on the top plots the relative FP drifts in meter per second as a function of wavelength. So these are the two same plots at the top, but at the bottom it's the order by order radial velocities from tau ceti, and as you can see, as a function of wavelength, it was showing the inverse shape as the Fabry-Perot drift, which is expected if you don't fit for this effect. And on the bottom right, it's the new pipeline version with the chromatic fit, and you see that there is no longer any wavelength dependence on the order by order RVs on tau ceti when you compare two exposures separated by roughly 3 years. So that's it. Thank you very much.
Thank you very much, Christoph. We started a little late, so maybe we'll do one quick question. Anyone in the room? Nem? You're
Nice talk. How often do you do that calibration process on Espresso?
Every night.
Okay, so that's part of the standard calibrations.
Yeah.
Okay.
Yeah.
all right. Thanks again, Christoph.
You're welcome.
Next up, we have Xavier Demus telling us about. Oh yeah, of course. Telling us about calibration.
Good. Okay. Thanks a lot. Let's try to move on, not to be too late. Okay. So I will speak about the calibration, what the wavelength solution scheme we have adopted for harps and harps nose, because we didn't have the Fabry Pro for a long time. The first Fabry Pro arrived in 2012, but really was really used starting in 2015. So we had to rely on other things. Okay, so this is just very to refresh everyone. The thorium spectrum, you have a few lines per order. Okay, it's not an étalon, it's not a LFC. All the lines vary in intensity. You also have some argon lines, so you just have to be careful not taking those because they're not as stable. You have a lot of lines that are blended. And what don't know with time is how those blends behave, basically. So it can introduce some velocity shift if you're not careful in selecting those. But basically, the idea is quite simple. You have those lines, you know what is the wavelength, you have the pixel position, and then you just, for each order of the instrument, you just fit a polynomial to that, and then you are able to get a wavelength for each pixel of your instrument. So very easy. Okay. But if you do that, the thing is, okay, then if you start to take into account the photon noise that you have for each of your spectral lines, when you go towards the edges of each order, due to the Blaze function, you don't have a lot of flux there. So then your polynomials are not well constrained. So then you can say, okay, but for a star, you don't have a lot of flux there as well. So it doesn't really care. But still, I will show some data where we can have deviation by 50 meters per second. Even if it's on the edge of the order, then when you include this in the entire budget, you can arrive to systematics of about 1 meter per second. So you have to still be careful about that. And then overall, if you do this for each order, normally we fit a fourth order polynomial, something like that, because you cannot really do more. 70 orders, it's nearly 300 free parameters. So it's really a lot of free parameters for a spectrograph that is not supposed to move that much in the end. Okay. So here you can see for different orders, from the blue on the left to the red, you can see what you can do with a wavelength solution where you fit each order independently with thorium lines. And you can see that on those edges here, you can see, so this is one month of measurement of the thorium, of the thorium. I just corrected for the drift, the absolute drift, but you see that the wavelength solution are not stable on the edges. Okay. Then you can use the solution that Christoph proposed. So it works well on Espresso. Unfortunately, on harps and harps nose, for a long time, we didn't have enough flux in the blue part of the spectrum. And in fact, you can see here, the blue part is more or less exactly the same as the other one, because in this derivation, I also included that if there was not enough flux on the FP, I was just relying on the thorium lines. So this was not really an option for hops and hops nose. So we decided to go with something else. Okay, so the idea was to reduce the number of free parameters in this, because I think there is just too much freedom there. And then to try to link the orders together, because orders that are close by together shouldn't have a big difference between them. So just by making the hypothesis, by knowing that the spectral graphs are extremely stable and so on, you don't expect the thorium line, the thorium spectrum, to move much from day to day. Okay. And you expect that this, if it moves, it's something that is very smooth over the detector. Okay. So what we used is, okay, this is the normal way to do it. Like you have different nights, you do a wavelength solution each night per order, and you arrive to those systematics there. Okay, so what we decided to do, okay, is that we have one night, okay, and on this night we say it's our reference night, and we do a wavelength solution there. In our case, we do a wavelength solution combining thorium and FP to have something in terms of absolute scale that is not too bad. And then what we do for the other nights, we just look to the drift of the thorium lines, by how much the thorium lines have moved. And you can see here, on the left, you can see an image of the detector with all the orders, all the thorium lines there. And what we did is that for each of them, compared to the reference frame, we just measured by how much they moved. Okay. In velocity or in pixel, you can do in any scale. And then once you do that, then what you can do is, you can see here on the right, we just fit a polynomial to that. So low order polynomial, 2D polynomial on the detector to be able to fit by how much those thorium line moves with time on the detector. And so then once you have this wavelength solution and then your polynomial fit, you can just take the wavelength solution of your reference, apply this polynomial shift, and then you have a new wavelength solution. And then with that, you go from 300 free parameters to 15 or 20, something like that. Okay. And then when you do that, you arrive to those type of residuals that you have between the wavelength solution, and you see it's much more stable. Okay. So here you have a comparison between the different methods. This is on Halverson's data here, so it seems to work very well. In terms of what is the gain by doing that, what we did is that we just compared day-to-day calibration and measure what was the offset between them. Okay, and if you do this with the order by order wavelength solution, you arrive to 75 centimeters per second. If you use the new drift map method, like we call it, you are down to 50 centimeters per second. So you are really able to reduce quite well the systematics there. Then the problem is, how does this behave on the long term, right? Because if on the long term your spectrograph moves a lot, then perhaps you can have some deviation and this polynomial cannot fit for all of this. So here I just took the detector, I divided in like 64 different cells, okay? And what I look over time, so here you have 10 years of Harp's nose, basically. And what I do is that I check the thorium lines, basically how they are, what the residuals of the position of the thorium line with what the wavelength solution gives me for those lines. And you can see that here for everywhere on the detector, it's very stable over time. So it really seems that even though the spectrograph have moved by perhaps 300 or 400 meters per second in absolute drift, we are able to recover this quite easily with only one wavelength solution and then just fitting for this drift map. Okay, and that's it. So I think this really improved a lot the wavelength solution on Harps and Harps nose by going from 80 to 50 centimeters per second night to night jitter, I would say. And then this can really help when you don't have a lot of flux, which is often the case in the blue part of the spectrum on the edge of the order. And I think this can also be applied to thorium FP wavelength solution, or also with the LFC, because often the blue part of the spectrogram, you don't have a lot of flux on the LFC. So this could be a technique that you could use. Thank you.
Thank you, Xavier. Questions in the room? And for those remote, we are watching both the Zoom chat and the Slack channel, so feel free to post questions there.
So how often do you remake a drift map, and like what drives that decision?
So basically, we do a drift map for every day because it's where like we have the wavelength solution of reference, and for a certain day, we just measure the drift map and get a new wavelength solution. And then overall, I have to say that so on harps nodes, we use only one reference in that case with the 10 years of the instrument. For harps, we use two because in 2015 we had a big intervention on the instrument. We changed the fiber from circular to octagonal. And the spectrum moved by 3 pixels on the detector, and the PSF is also different, so it's not just a shift. So in that case, we use 2 wavelength solution and like basically 2 different instruments. But so twice on harps and only once on harps nodes.
Any other quick questions? Gaspar, you want to come up? I have one quick one, which is, so you're sort of using this localized drift and then doing a 2D polynomial to that before redoing the full solution. Is there an advantage to doing something non-parametric? So you're measuring a localized drift for your thorium line. Can you just use that as a delta for an existing solution? Right. Right. It works. Okay, very good. Well, thank you again, Xavier. Next up is Gaspar, who will. Sorry. Next up is Gaspar, who will tell us about 2 combs. That sounds nice.
Okay, thank you. Good afternoon. Yes, I'm going to talk a little bit about the ARPS and the espresso laser frequency comb. Unfortunately, I'm not going to offer solutions, but I'm going to show you the troubles that we are having for various things. The 2 combs are now quite different because recently we have upgraded the espresso laser frequency comb with a new fiber that allows us to go much more into the blue. We can actually achieve a wavelength of 400, a bit short of 450 nanometers. While in the case of ARPS, we still are up to 500 nanometers. Essentially, we illuminate with the comb almost only one detector, the red detector of ARPS. Meanwhile, as there are no picture involved, I comment that as part of the espresso upgrade, also the room where the espresso laser frequency comb has been upgraded and stabilized in temperature, so that now we are at the level of a fraction of a Kelvin stability, while at the same time, just out of these days is the action that we took to stabilize also the ARPS laser frequency comb with a chiller that will try to maintain the temperature of the breadboard where the optics sits as stable as possible. So what I'm going to try to face in this brief talk is what we can probe, what we can understand using the laser frequency comb about our system. And one is, thanks to its exquisite lines, extremely narrow, unresolved by our spectrograph, we can really study the line profile across the detector as long as we have laser frequency comb lines, and we can try to understand whether it changes as a function of position, as a function of time, or flux. And then the 2 big questions which brings to precision and accuracy of our wavelength calibration. This is not precision or accuracy of the comb itself, but rather of what we see in our system, which is quite different. So first thing, this is just an analysis, a moment analysis of the laser frequency comb lines in the detector. There is no extraction here. We are just looking at the raw data of one specific order. On the top is the first moment, the second moment, and the third moment, which express the asymmetry of the lines. So we learned several things here. Well, the first moment is actually the difference. What you see as a first moment is the difference between the peak of the line and the first moment, actually. And you see there are some interference pattern, more a pattern that you have typically when you try to superimpose two different grids. The second order, so the width of the lines changes. This is the line profile, purely the instrumental line profile, and they are asymmetric, and the symmetry also changes as a function of position in the detector. You can see here again the third moment in 2D in the X and Y, and for the various orders of this specific chip, and you see that it changes along the face of the detector. And you have to take this into account when you want actually to fit properly your lines. We tried to understand what kind of function we could use for the fitting, and we explore various options. And at the end, the option that we found more consistent with the data is that of a constrained double Gaussian. So it's the main Gaussian for the peak, and then another Gaussian which takes care of describing the tail. Looking at the third moment, one thing that we learned, and the third moment is really a flag for this, is effects like nonlinearity of the detector or charge transfer inefficiency. On the left plot, what we see, we divided the detector in stripes, and we take the leftmost stripe of, I believe, 1,000 pixels, and the rightmost stripe of another 1,000 pixels. This is a work by my student a few years ago, Fei Zhao, and we looked at the third moment in these two areas, and we subtracted actually one from the other. And what we see is that we definitely have a systematics left to right. So the lines on one side of the detector, they have a different symmetry. And this is even more pronounced when we play with the absorption of the laser frequency comb line. And then we see that this number, the average over the full detector, it changes quite a lot when we change considerably attenuation. And this is really going in the direction of what we expect from charge transfer efficiency. So it is really critical to correct for this. Let's go to another thing that laser frequency comb can teach us, precision of our wavelength calibration. What we are doing here is I'm comparing the wavelength solution on fiber, well, the laser frequency comb line position on one fiber with respect to the other fiber, and I'm subtracting the drifts from them. So ideally, what I should be able to see is a flat line at zero, because the lines move together with both on both fibers. That's not exactly what I see here, because we have some effects like speckles, modal noise, etc., that we have to take into account. But we do see that as we so we increase the number of exposures. Let's start from here. We actually managed to go down, all the way down until centimeter per second. But the main point I want to make here is that yes, we can reach photon noise, and we routinely reach photon noise, but not always. Every once in a while, we have a hiccup of the system. Something stops working. We ask for rescue, and the rescue comes, but we really have to be very vigilant, very attentive, because at times the system seems to be working. We have light, we are happy, but then when we look into our precision, we see that we suffer something. There is something that needs to be still fixed. And then we go from one configuration to the next, and we start trying to understand where the problem is. Finally, we manage to reach again the photon noise limit. It's nothing simple. It requires quite some effort and struggle. The unexpected problem that I found was about accuracy. So this in green, you have, well, on this part, you have the thorium solution. This is just the blue chip, let's say, of ARPS. These are ARPS data. And on the right chip, what we have is the laser frequency comb wavelength solution. And actually this is the difference between the thorium and the laser frequency comb wavelength solution. This is one thorium for reference. It's not the same one I'm using here. This is why it's not 0. But what I see at the beginning, taking the number at face value, this is the difference that I have between the laser frequency comb and the thorium wavelength solution. And this is at 180 meters per second. So trying to understand the origin of that, and then we realized that the anchor frequency, it was being given to us from the system in a wrong way. There was a wrong computation. So we had to go and correct for it. This correction was made, and then we end up in the blue line up here, which is certainly much better, but is not yet at the level we hoped for. And it is actually at about 20 meters per second below. So we're trying to understand that one. We still didn't understand it. In desperation, we even tried what happens if we change just in our scheme of things, in our computation, if we change the repetition rate, and we see that that could be compatible with a change of repetition rate of 2 kilohertz, but doesn't really make much sense physically speaking. And if we look over time, this is quite stable. It is an offset of 18, almost 20 meters per second between the thorium solution and the comb solution, with a standard deviation clearly dominated by the thorium. And finally, another issue, looking at the difference between the two fibers, I want to monitor this in time. We had the laser frequency comb that was working for 6 months in a row, was a great victory. And this allowed us to see how this is evolving with time. And to my surprise, I saw that it was not flat at all. There is actually a drift. This discontinuity here is a specific event. We had a problem with air conditioning that we later recover, so this is understood. But there is a drift which is suspicious. At that point, I also wanted to double check whether it was an issue with the comb, and we looked at the thorium, and this is the same measurement taken with the thorium. You clearly see much stronger noise, but there is still the drift. It's a drift of about 3 meters per second in 6 months, so on average 2 centimeters per second per day. What this is non-common path drift or changes. So that means even if we correct for simultaneous reference, we will make an error of about 2 centimeters per second per day. No, not that dramatic, certainly for ARPs, because next day we take a new calibration, so with 0, this offset. But if you want, if your budget is that of few centimeters per second, then it may be an issue. And I leave you with the conclusion. So we need to.
Thank you, Gaspar. Very illuminating. Very interesting to see. Questions for Gaspar? Chad.
This may be more complicated than we can get into now, but I want to learn more about the absolute offset and the fundamental frequency problem that you were having and then solved. Because I need to understand the origin of that and whether it's intrinsic or some misinterpretation, because it probably affects all of us.
Yeah, I believe it may affect all of us. I quite spent some time thinking that must be the thorium, because you know that the thorium lines, they are not that well known. They have errors of the order even 100 meters per second, but this is systematic on all of them, all wavelengths, so I tend not to believe it. So still interacting with our supplier to understand whether there is possibly an origin which comes from the comb, from how the anchor frequency is computed. Still have to understand that.
Right. One more. Oops, sorry. One more question. Christian, I think you had your hand first. Oh, yeah.
Just to comment on that, because there was the talk by Tobias Schmidt this morning. In espresso, we also see 10, 15 meters per second. So that might be the same reason. And in that case, it would be linked to the PSF, the fact that the convolution is not the same if you use a non-resolved or resolved lines and so on. Sorry.
My question. Gaspar, you said that you can fit the PSF because the LFC lines are so very, very narrow. But in principle, we can make Etalon lines also nearly unresolved. And how narrow do lines need to be for you to get a good line spread function model? Can you back it out if an Etalon line is a quarter of a pixel, or is that still too broad?
The best solution you have is if you have unresolved line, clearly. Then do your best, and yeah, you will have your line profile will be convolved with your best, let's say, and with.
All right, let's thank Esper again. All right, next up we have Mikhail Cretonnier. He's going to tell us about calibrating using stellar observations. Quite interesting.
Hello. So thank you, everyone. So today I will try to convince you that you can somewhat calibrate your instrument with stellar observation. And I know that for some of you, I will look like a heretic, right? And so that's why I put a question mark on my title. So please don't burn me on the public place. So there is different way to correct for your wavelength solution. I think there is basically 3 schools. The good way, which is the one that Xavier just showed, so you really try to improve at the DRS level the extraction of the wavelength solution. Of course, there is a different method, also the way of Lily, Excalibur. This is really good. There is the brute way, shown by Trifonov et al. In 2020, where you basically try to average all your stellar observation to somewhat recover your instrumental systematics. So I will try to convince you that it's wrong to proceed in that way, simply because when you average all your stellar observation, you also have the average of all the planetary signal, you have the average of all the activity signals. So below the meter per second, it doesn't work. What is right, however, is that intuitively the instrument is common in all the stellar observation. It is the only part which is common. And I will show you what is the right way to proceed. And the argument is that one. So what you have is that you have a systematic on your detector. It can be either a mix of 2 systematics. So here you see if you are on red, you have 1 systematics. And if you are in blue, you are another systematics. What is happening is that when you have a spectrum, you are with your stellar lines, you are going to go at some location of your detector to pick what is the systematics at that location. Now, this is true for 1 star, but if you have another star, that star doesn't have the same systemic radial velocity, so it's slightly shift. Also, that star does not have the same effective temperature, so the weights of the lines are changed. And also, it doesn't have the same chemical abundance. So even if the common effect is the same on the detector, in the time domain, the effect is not the same. That's the important point to recall. And so the idea is that if you look the individual line by line radial velocity, if a bad wavelength solution is acting in that way, so if all the lines are affecting in the same way, I have no solution for you, unfortunately. The good point is that this is not what a bad wavelength solution is. You rather have something like this. So some lines are more affected. This is what Xavier showed just before. On the side of the detector, you have those wiggles, and you have several lines that are affected by those wiggles. And so you can try to use that to decorrelate or to correct for the effect. And so the idea is that you have a common effect, which is the planetary signal on all the lines that you see on the left. And then you have some systematics that change from line to line. And you also have a white noise component, which is the 3rd column. So what you can use is that if the problem is somewhat linear, or if some lines are more affected, you can use a PCA. Again, I really like PCA. And here, that's the idea. When you perform a PCA, the planetary signal, which is the barycenter of the cloud, is not sensitive to planetary signal. So your PCA will only recover the instrumental systematics, which are simply the elongation of the axis that you see. So that's a good point, because with your PCA, you won't be affected by the planetary signal. And so there is one drawback with that, is that in the model that I showed you before, I neglected one component, which is now the 3rd column, which is the fact that each of your stellar line can be affected by different systematics. You have the tellurics, you have stitching effects, so you have peculiar effect that you need first to correct if you want to use such method. And so that's why I have developed Yarara. And here you see some of the systematics that I mentioned. So you have lines that are contaminated by telluric. So we have to correct for them. We have also the stitching effect. We have also to correct for them. And we have also ghost contamination that you also need to correct if you want to perform your PCI. Otherwise, I let you discover what your PCI will give you if you don't correct for them. And so this is the method that I have at the moment. So this is the results. So if you perform a PCI on the line by line on harps, this is the components that you have. So on the top, you have three components of the PCI. This is the time coefficients. You have the periodogram of the time coefficients, and you have simply the amplitude coefficients on the detector. So here are all your stellar lines. And what you can see is that the first component that we detected by the line-by-line PCA was that drift with jump. And that jump corresponds exactly at the moment where we change the thorium lump on harps. We also detect a component which is smooth on the detector. So again, this is an instrumental systematics because I don't put any constraint on my PCI. So my PCI is free to fit what the PCI wants to fit on my detector, and it provides me something smooth. And the third component that you see here has also 1 year power. So when you see 1 year power, I mean, you expect instrumental systematics, of course. Now, this was for 1 star. And the good is that when we perform it for different stars, so here you see 3 stars now, we recover exactly the same components. So you see, we recover the thorium argon aging of the instruments. We also recover that component, the smooth on the detector. So we recover all of them. And so it led me to that idea that, okay, what you can do if you have several stars, if you want to merge them, is to reconstruct the detector map of the systematics. And this is what is shown here. So here you have 20 stars observed by harps, and you can simply now put the effect back on the detector, and you can fit a model for them, which is on the right. And as soon as you have those maps, you can try to use them to derive back again the time domain coefficient for each of these stars, depending on where the lines are on your detector. So all of that is based on a paper that I'm still in preparation. It will be soon published. I mean, soon submitted at least. And so what are the pros and the cons? So the pro is that you can use that basically to disentangle non-Dopplerian effects. So you are not affected by planetary signals. You can also try to use that to merge all your stellar observation, which is something which is quite nice. So you can use all your stars in your program to correct for it. And also it's a multilinear problem by construction of the PCI, which is also very nice. Now, of course, there is cons. And I mean, the main cons is that you have to fit back the component in the time domain. And so it means that you can absorb signals because you fit in the time domain. So if you don't include the planet in your fit, you will absorb for it, of course. And also it's very actually sensitive to local systematics. So you have to correct for all the issue on each line-by-line radial velocity. And actually another issue related to that is that sometimes you have large variance in your cloud of data, but with a really small mean effect. And so sometimes your PCI components that you derive are completely, in a sense, useless. And you have to derive a lot of them before to find one which is relevant. And related to that, you have those interference patterns that are really a nightmare when you do line-by-line PCI. And I think I will conclude there. Yeah. Yeah.
Questions?
Yeah, wow, that's really great. The question I have is, so you're doing basically the combination of different stars. Once you have the different components calculated on each individual star, is there a way to actually do this in the process of calculating the PCA itself, so that you inform the model already at a stage where you have different observations? As you said, I mean, each system might have some systematics that are hard to capture by the PCA, but if you look for something common, right, that shows up in all systems, maybe that additional dimension, so to speak, of having at that fitting stage already different spectra might help. Is that computationally too expensive, or?
I'm not sure to have fully understand the question, to be honest, but is the idea to already merge all the stellar observation at the PCA level, right? So this is quite, I think not necessarily possible because, for instance, if you look about the dimension of your data set, this is time versus number of lines, basically. And those times and those number of lines are basically changing from star to star. Typically, stellar lines are not the same. So either you have to take the intersection of all your stellar lines. For the time, it's not a problem. You can simply stack your matrices together. But for the stellar lines, it's an issue. So you should take a subset of stellar line common to all the stars if you want to do that.
Thanks, Mikhail. So when you have those maps, then you derive some time series and you correct for those time series in a linear way. And you say there is a problem there because you could have some collinearity. But now that you have those maps, what the spectra are given at the same position as those lines. So couldn't you modify the spectra with those components that you see here and then derive the velocity from those?
So no, I cannot do that. Because the color code that is showing, I mean, when you perform a PCA, you always have a degeneracy between the vector length and the coefficients. So basically the coefficients are unitless and the vector are unitless. So you need a way to fix the amplitude in some way. And that I never managed to do it actually. So if you can then give a kind of ruler, I mean, to your coefficients, yes. If you can stretch them to a kind of accurate, in an accurate way, yes. But at the moment, I am not able to do that. Here, everything is precision, not accuracy.
All right, thank Mikhail again. Got Lily Zhao. Scroll past all that one. Perfect. Talking about the express wavelength solution.
Great, thanks, Dan. Yeah, so I'm here to talk about the express wavelength calibration and also this method I just developed called Excalibur for wavelength calibration in general. I think the key thing to keep in mind about the express calibration is that we have a thorium argon and an LFC, but we don't use our simultaneous fiber. And so instead we take calibration images, we'll take 3 LFCs back to back, wait 30 to 40 minutes and take another 3 LFCs. And in this way, the calibration images are projected onto the exact same pixels as the science images are, which is why we choose to do that. And so our wavelength calibration has to both go from calibration lines to all the pixels in between, but we also have to go from calibration images to the science images that we take. So our first crack at this was using polynomials in every which way and form. And so here I'm showing our different calibration lines with thorium argon in the LFC region there. And it's laid out in pixel on the X direction and absolute order as our fallen for the Y direction. And so we fit this to a 2-dimensional polynomial, which is 9-dimensional in both ways. And then we evaluate that at each pixel to get the pixel information for all of the pixels. And to translate this with respect to time to get it to our science images, we then take every single coefficient of our 9th degree 2-dimensional polynomial. And so on that side, I'm now showing each little spot is like the coefficient with respect to time. And we fit that coefficient with respect to time to yet another polynomial. We evaluate that polynomial with respect to time. And then that polynomial tells you what the pixels are. So I've already hated how many times I said polynomial. No longer sounds like a word. And so when I was working at the Center for Computational Astrophysics, I came up with a different way of wavelength calibration. We called it Excalibur, which is a non-parametric hierarchical model for wavelength calibration. So the hierarchical part of it allows you to use all of your calibration images instead of just one or the ones that are closest to your science data. And the non-parametric allows more flexibility so that you can correct for more small scale differences in your detector. And so the thing that it takes in over here is this array of line positions. So for each of your calibration lines, uniquely defined by where it falls on the detector, you find out what X position it is and what Y position it is. You take all of the calibration images you have and you do some sort of dimensionality reduction. You can pick your favorite to figure out what sort of basis vectors you have that describe the variations in your instrument. So for example, here I've illustrated the case where maybe your calibration lines vary in this way, and it indicates a tilt in your detector. or it tilts in the other direction, or it rotates somewhat. And because you have this stable calibration source, by seeing where those lines fall in your detector throughout all of your observations, you pick on which ways your instrument is varying. Then when you want to calibrate your instrument at any given point in time, all you have to do is figure out where in this variation space your instrument currently lies. And you can use that to recreate the calibration lines you would have seen if you had taken a calibration image at that time. So doing this allows you to learn how your instrument is varying, and also allows you to recreate denoised higher signal line positions from understanding that variation space. And when you have these denoised lines, you can then do a non-parametric rather than a polynomial, for example, interpolation between the different lines, and use that to derive a wavelength calibration for each pixel in your detector. And so because it's hierarchical, you get more force than just one LFC at a time. You learn about your instrument, you learn more about where the lines are, and you get a better, more precise wavelength calibration in the end. And so now I have some figures so that you all believe the things that I'm saying. And so I applied this to Express. And so here I'm showing for dimensionality reduction, we use principal component analysis, and I'm showing the first 9 principal components for if you run it on months of Express time. And so you can see how in the first 2, we get these clear gradients, right? Express detector seems to be flexuring along this pivot point. And for the second component, we see maybe it's flexing in this component. And so maybe that relates to how the detector is mounted or how the detector is moving with respect to differences in time. There's also some maybe like second order degree here. And if you get too high dimensional, you see that it just becomes dominated by noise. And so here we've learned a little bit about how Express is varying, and also maybe things that we want to check next time we want to fabricate a similar instrument or use a similar detector. We can also see the amplitude of these variations with respect to time. And so now I'm showing on the x-axis time, and on the y-axis is the amplitude of the first principal component, so the degree to which that variation is present in your data. And so that's shown in blue, and in orange is the optical bench temperature in our telemetry. And you can see that that variation tracks the temperature almost exactly. And so Express is passively controlled, and so I think that's why one of the major dominants of variance is due to this temperature, but we don't have to deal with nitrogen swings, things like that. And because we have this LFC information and we're using this hierarchical model, this temperature difference is something we can now calibrate out with our wavelength calibration. And of course, using all the LFC lines gives you more information about where each LFC line should be. So here I'm showing for just one order where all the LFC lines fall on the x-axis with exposure number on the y-axis, so kind of time, right? And in the colors are the corresponding wavelength, and in black are when your LFC lines just didn't show up because it didn't feel like it that day. We all have LFCs, we get it, right? And so if you were treating each LFC observation by itself, those black squares would be information that you would just lose. You would get no information about what's happening in that part of your detector. But if you look at this figure, right, you can see a black square there, and you can see that the line falls there before the black square, and it falls very similarly after the black square. And so you could very easily draw a line as to where you think that line should fall, given the before and after exposures. And so bringing in the hierarchical component makes that into an algorithm and allows your wavelength calibration to make the same kind of calculation, fill in blanks where lines might be missing on one off, and also denoise all of the line positions where they are missing. The second part of Excalibur is this non-parametric aspect. And so I'm going to start running through like a series of tests where I use a subset of lines to create a wavelength calibration. And then evaluate it on a different set of lines. And so here, for example, I'll either evaluate the wavelength solution on the thorium-argon lines or every other LFC line and evaluate it on the remaining LFC lines. And so on the y-axis, I'll show the difference between the actual wavelength value for the LFC versus the constructed one. And so if you use the polynomial, the residuals you get are the dark orange. And so you can see that they fall pretty low. And if you use a non-parametric model, the P-chip, they're huge because we're using the thorium-argon lines here, and their uneven spacing doesn't provide enough information to fully constrain this non-parametric model. But if you use the LFC lines instead, now when you have a polynomial, you get almost the exact same shape as you do with the thorium-argon lines. But if you use a non-parametric one with the LFC lines, it's the much darker line that falls right along 0. And so here I like to point out that using both the thorium-argon lines and the LFC lines with the polynomial, so the dark orange and the light blue, the residuals even have the same shape. So even though you spend all this money on an LFC, all these blood, sweat, and tears for keeping it up, you're really not getting more information from using your LFC lines if you're just fitting it to a polynomial. Similarly, if we take that to a 2D thing where now I'm using like the even LFC lines to construct wavelengths for the odd ones and vice versa, the 2D appearance looks like this. And you can see we have all these like vertical structures on the detector that we've actually traced back to things that variations we see in our Mengen mirror somewhere upwards of the optical path. If you use a much more flexible non-parametric model, the residuals go almost to zero. And so by moving from a polynomial or a parametric model to something much more flexible, you're able to correct for a lot more of these like bespoke detector effects that I'm sure we all have in our optical paths. And so when we apply this to express data, if you look at compare the RMS of the resulting RVs using the polynomial on the y-axis versus using the Excalibur RVs on the x-axis, you see that Excalibur wavelength calibrations uniformly reduce the RV RMS by 10 to 50 centimeters per second in some cases for all of our targets, showing that this really was removing some sort of like red noise source in all of our data that was due to the instrument that would otherwise just be there. And so for future work, I think there's a lot more that could be done with Excalibur. There's a very easy extension to simultaneous calibration that I just don't have the data for. I think Etalon might be a little bit trickier, but there's a way to fold in the free spectral range to your model that could make that work in much the same way. And we also have this hokey idea where maybe the trace positions themselves provide enough information to show how your detector is varying, and then you could just use those rather than LFC positions to just always get a simultaneous calibration with any observation you take. I think the method could be made more powerful if you incorporate more housekeeping data. So if we train the calibration state to the temperature and told it explicitly that information, it would do a better job of figuring out where in the variability space it was, and therefore provide a more precise set of calibration lines afterwards. And if you really are an optimist, in certain ways, principal component analysis picks up on variation. And so it might even work better with less stabilized instruments if the variation is larger. And so it's something that I think could expand well beyond the EPRV work. And so a lot of these thoughts about how to expand it in future directions are in the paper that I provide the archive link to, and the code is publicly available in this GitHub repo. So thank you for your attention. I'm happy to take questions.
Thank you, Lily. Questions?
Hi, great talk, Lily. I'm curious, as someone who knows very little about PCA or has never had a good opportunity to dive into PCA, can Excalibur, does it take in any information on the uncertainty of like the centroids of lines? And kind of on top of that, are you ever worried about the PCA just overfitting at the end of the day?
I'd say PCA is like base level linear dimension reduction. So that the way that I've implemented it doesn't take into errors, but there's ways there's heteroscedastic matrix refactorization where you could include the errors and other maybe non-linear things that could take into account more effects. The thing you have to be careful about with overfitting is it's not overfitting, but it's including too many dimensions. And so the way that we're using this dimensionality reduction is to denoise it, to only focus on the variations that we care about. And so if you use too many principal components and you're reporting in noise, or it's picking up on the wrong variations, that will continue to be represented in your model when it's something that we'd rather avoid. And so there is some coercing you have to do to make sure that it only picks up on the variations you care about.
One more quick question.
Thanks, Eddie. So if I understood properly, you only apply Excalibur to the laser frequency comp data. What do you do in the blue in that case?
Move on. Thanks again, Lily. Next up, we have Jason Reeves from Menlo. All right. He's going to tell us all about recent developments at Menlo Systems, a company we all know and love.
Hi, I'm Jason. Thank you for being here and letting us give a talk. I know we're just the laser company, and so this will be a little bit different flavor than what we've heard earlier in the Splinter session. My colleagues, Tilo and Ronald, both wish they could be here, but unfortunately, they had other commitments. We started our journey in this about 15 years ago, and we started with a simple request from this community: can you make a calibration source for a shell spectrograph? And well, we all know how that turned out. And over the years, what we have discovered is kind of an ideal set of specifications that we need to hit. We need to be somewhere between 10 and 30 gigahertz. We need good spectral coverage in both the visible and the near IR. And you want decent amount of power per comb line. One of the things that we've talked about in this is the short-term and the long-term stability. We say no drift, and we've seen that there's still discussions going on about drift. So we're always there to help. We're always there to learn new things. But in the atomic world, we actually see no drift. So we're making progress. The last point is price. Budgets aren't infinite, and we are still rather pricey. That being said, we have 12 of these in the field, and as we've started, they've gotten better each year. So if you see yourself up there, you kind of know what revision you're at. But we started way back in the about 2010 with a visible comb spaced at 5.4 gigahertz for Tenerife, Spain, and we've moved on from there. The first two systems that we actually delivered were for HARPS and this one in Germany. And these are what the original systems looked like. There were two big racks, two big boxes. A lot of those still carry over to today. And the general hardware, we've got our comb, we've got a cavity to increase the mode spacing, we've got amplifiers, we've got a tapered PCF to get us all the wavelengths that we want, and then we split this and we flatten the spectrums. But we haven't sat still since we started these projects. Things have always gotten better. Our most recent efforts, we've taken our F2F interferometer that locks our comb. We now have a higher signal strength and more power, so it locks better and stays locked longer. We've also gotten rid of these filter cavities. We've went from a 20 by 30 centimeter filter cavity to a 4 by 4 centimeter cavity. And we've also been working on the fiber. I've been guilty of overselling this fiber in the past, and so I will be careful. And some of you will say, hey, look, I know I did it small. That's 400 nanometers there. Yes, we do have a fiber that will go down to 400 nanometers, and we have just submitted a paper that says we expect 1,000 hours at 420, and we've seen as a science experiment that it works. So we are progressing along that line and are trying to get the blue light that you all need. With all of those implementations, our latest one, this is KPF. We've dropped down to one single rack. We've changed a bunch of the electronics. We've changed how you can talk to the system. And you can see the boxes here have gotten smaller. These are the 4 by 4 centimeter cavities, the oscillator, and over here is our F2F interferometer. And then we have our spectral flattening and our amplification over in the other box, which hasn't changed much. So as a company, we like to do the science and we like to collaborate with this community, and we have for quite a while. And so originally we were really just trying to replace the thorium argon lamps, but along the way, there's been many other technology advances that we've seen. And so what we've done is we put together a little, how do these all compare? And these, I'm speaking to the experts, so I won't go through much of it, but we still believe that the laser frequency comb checks all the boxes, except for the price. It really is short-term and long-term stable. We can get into the visible. We started with the visible, which is really a hard thing to do, and we keep pushing down that spectral coverage. And you all are well aware that it's not just a light bulb. It takes some work. But also in our company, for other applications, we have a very vested interest in microcombs because combs on chip hold a lot of advantages. So we've been playing with this and thinking about how can we invent the next frequency, the next astrocomb, which would be simpler and more easy to use and just overall better. So at the moment, we can take something that's our smart comb. It's a 3HU unit. It's got, this one's based on erbium. It's a fully locked frequency comb, and we can pump either a cavity, an EOM, or a microresonator. And then we can use our back end of our amplifiers and our flattening units to go ahead and amplify and flatten. We have successfully done this with our smart comb. We pumped a microresonator, which gave us absolute frequency lines that were spaced in the 20 gigahertz range. And this has worked well. But as you can see, it is in that kind of NIR range. The microcombs at the moment aren't as broad, but this is a pretty cool result and fairly large for a microcomb. One of the other things that we've been doing is, since we can use this back end now, we can put microcombs, EOMs, or laser frequency or laser oscillators on the front end and do comparisons. And so we have started to make some comparisons of the different types of combs that we have our hands on. So EO combs are pretty easy for us. We can grab some EOMs and do some things in lab. We've checked the silicon nitride Kerr combs and the crystalline combs. And so this is kind of where we see things going, is toward a simpler front end. We don't know if it will be simpler at the moment, but we will certainly have something. If you do buy a frequency comb for astrocomb applications, the back end will be good and will be backward compatible. So with that, I will say thank you. And I will say, if you have a comb and you want to talk about problems that you're having or how good it's been acting for 6 months, please come and visit me. If you need support, come and visit me. I can connect you. Most people know Tilo very, very well. He's our magician when these things happen. But the nice part about being in sales is that I have arms to twist and I can get you any information that you may need. So hopefully you have a vision of what we're doing. If that sparks imagination or questions, we're happy to help.
Very good. Questions? I'll note, this looks like Tilo's cell phone number for anyone who's interested. So if you don't have it, there it is. Oh, he's lying. Questions?
Hi, thank you. You have the filter cavity and then the broadening. This has been a choice since the beginning. And if I remember correctly, it's because of the group dispersion delay, which so you cannot filter afterwards over a broadband. But there are now, if I understand correctly, this is being done now. So what happened in between?
That's a great question. So we have always chosen to do our filter cavities first and then go through our tapered PCF, depending on how good you can make your cavity. So basically what you do is you do a lower finesse cavity, but you do it for multiple wavelengths, and that gives you a windowing function. And if you can make that significantly broad, it works. Early on, Harvard had done some of this, Walsworth had done the cavities after a TISAF comb. And it turns out if you can get the right mirrors and whatnot and work hard on the cavity, it works well. This for 1.5 and then going into the visible, or 1 micron, and then going into the visible was just easier for the cavities. And the PCFs, because we're getting such a broad wavelength out, this was how we decided to handle that. But certainly you can do either way. Yes. And it lets us fiber couple in and out of our cavities as well.
Thank you. So the bottleneck in going bluer, as far as I understand, is the PCF and the color centers that form in that fiber. Do you still see room for improvement from the fiber perspective? Is that still promising, or have we reached the end of the road there?
So this 420 is pretty promising. And this paper actually starts to talk about what actually causes that photo damage. It looks like 4-photon absorption. It also compares if you move to different materials, what will happen. So what we've done is we've moved away from a PCF to a blue enhanced fiber. So it's no longer a solid core fiber. It's still tapered. We're still working on it. The question is, how far can we push it? If we need to go under that, one of our current thoughts is to do an achromatic doubling solution. So take something that is in the kind of 600 to 800 range, go through a doubling crystal and do it achromatically and get it all to double down. And then you get that 300 to 500 range. So we are playing with different options, but yeah, we're still at the very forefront of the science on the PCFs that we're using.
All right, thanks Jason again. All right, next up, Nem's going to tell us all about spectral flattening on a chip.
Yep.
Do you want to do the slideshow? Sure. Oh.
Okay, well, thanks for the invite to talk today. This follows on nicely from the previous talk by Jason. Yeah, as we know, in astronomical applications of laser frequency combs aren't flat. This is a spectrum of the PARVI EO comb. I'm not going to pretend this is a great comb, but the point is that you see the spectral variation in intensity. In this case, it's 45 dBs over 400 nanometers, which is obviously an issue if you're trying to detect those lines with your detector and maximize the signal to noise. On the right, I'm showing you a homebrew flattener that was built by the team, occupying about 1 meter by ½ meter, and it typically, extracts the light out of the fiber, disperses it, uses a spatial light modulator to control the amplitude of each spectral channel, shoves it back into a fiber, and then takes it to your spectrograph. So there's quite a few bulk optic components, and Menlo will happily build you that and incorporate it into a small box. And if you're in the infrared like us, it's going to cost you $250,000 because we just bought 2. So having said that, someone that I work with, I have no idea what's going on with this. I clearly don't know how to use a PDF reader. So we're going to stay in this view. Can you guys online see the screen? Okay, great. So Chaz Beichman knows that I've worked on photonics for a while and sort of came to me and said, hey, do you think you could put this on a chip? So we sort of did that. We drew this on a napkin and it does exactly the same thing as your flattener. Up the top, you use a photonic component called an array waveguide grating to split the light into spectral channels. Then you use Mach-Zehnder interferometers to control the amplitude per spectral channel. You put phase shifters at the end to rephase everything. And then you use a second array waveguide grating to recombine in a single output channel. So yeah, you basically created a 20 baseline interferometer. So we went ahead and built that. This is a GDS file. I'm used to a plus button appearing here so I can zoom in. This is a GDS file showing you the chip that we built. This is silicon nitride based. Everything in purple or pink, whatever, is the actual device. So you see the whole chip is 32 by 8 millimeters in size. And this is the this butterfly looking thing. That's the dispersion grating. And then you have Mach-Zehnders at the bottom, thermal phase shifters at the top, and then the recombination arrayed waveguide grating in the top right-hand corner. The gold squares pads, those are the electrical connections to the chip. And this D3, D2, and test structures, those are all individual components for us to just test things to validate it because we didn't believe this was going to work the first time we did it. Right. So this is the design of the arrayed waveguide gratings. We chose to hit it to make a device that works over 400 nanometers. We have about 4 dB loss at the peak of the operating mode for this device. And when you double pass it just through the two AWGs, you sort of get about 7 dBs loss at the peak operating wavelength, and then closer to 10 at the edges. And this is a property of the silicon nitride, and the fact that we're getting a little greedy with bandwidth. You can optimize things by changing materials, but silicon nitride was convenient. These are our Mach Zenders. They're pretty straightforward. Light comes in at this port here, splits 2 ways. If nothing was done to this, they'd be perfectly balanced, and the light would recombine here and continue on. But we have this gold electrode or chrome electrode over the top of one of the waveguides. And by applying current to that channel, we can adjust the phase through thermal heating. And I know people are thinking, well, that must be slow. Not true. On a photonic waveguide of this size, we can modulate that at faster than kilohertz speeds if we wanted to. We don't, of course. And then the question is, what do you do once you've made the light interfere here and you've either rejected it or accepted it? So we have a multimode interference coupler with a drop port to remove any of the unwanted light, which you could use and exploit for tracking or something else. We have ideas for that. Anyway, this is the device when it was delivered. There's some fantastic companies in Europe. This is Lyonics, who fabricated the chip, Fix, who did the packaging, and Bright Photonics, who did the design work. And the whole thing, as you see here, is about, it's not very big. It came with a V-groove array on the side with fibers coupled into it, microwire bonding to a PCB. So we just basically plugged cables in and started driving things. So we didn't have to mess around with any of that stuff. We just outsourced all that. I will say, in a previous life, I used to develop photonics. I don't do that anymore because it requires a massive lab and a huge amount of people power. So I try to outsource whatever I can, and I focus on the testing and functionality of these things. So here are some results I'll flick through. This is showing you the individual output channels of the arrayed waveguide grading test device. The random curves at the bottom is our variable noise floor and our Fourier transform spectrometer. So it almost looks exactly like theory, 20 nanometer wide channels. And then we'll flick down to this one. This device. This here is showing you one of the devices. The wiggly curve is one of our devices that's back to back to arrayed waveguide gratings with some thermal phase shifting in between. And what you're seeing here is that at the spectral channel, there is no modulation because we're not modulating the amplitude, we're modulating the phase. So it's where that spectral channel interferes with its neighbor that you get the modulation in intensity. So it looks fang-like because it's on the two sides. Anyway, this is sort of the main result here. So what you're seeing here, the green curve at the top, the wiggly green curve, is when we use the full device. And what I did is I throttled all the channels to maximize throughput, but keep it as flat a spectrum as possible for the superluminescent diode. The purple curve is when I deliberately tried to phase everything in such a way that I turn off what light is transmitted. And the difference between the purple level and the green level is about 38 dBs, so almost a factor of 10,000 suppression. The red line is me just picking a level in the middle and just trying to flatten the spectrum to that point. And your blue reference line at the top, that's the insertion loss for the device. So the green curve to that curve is about 10 or 11 dB. So you take a factor of 10 hit in throughput through this device for a single polarization. But we're not really trying to optimize for that, given that we throw away a lot of light with the LFCs we use anyway. This is the stability over 24 hours, and it really varied, like very minor variations, and most of them are probably associated with a light source more than anything. Briefly, here's some testing with a laser frequency comb. During this publication, we only had access to a pre-broadened comb, so you see the sort of like the sync profile of or the sec squared profile, whatever it is, of the laser frequency cone. And they used a grading to notch out the pump region. So it's a funky looking structure. The orange line is our maximum throughput curve through the device. So that's the 10 dB lower. And then the green and the red line was me again by eye arbitrarily trying to flatten the spectrum. The blue shaded regions are showing you a 5 dB sort of bandwidth. And that was the requirement I was given to, like, hey, can you flatten the spectrum to about 5 dBs? And so that's what we did. Power handling, we managed to remove all the attenuators and put up to about half a watt of power through the device. It didn't release any blue smoke. So it seems to be fine and still operating. And this is what it looks like when you take the orange curve and you just take two of the Mach-Zehnder channels and you drive them down as far as you can, then you take a different spectrum. So everything normalizes out and you really do get 40 dBs plus of dynamic range on those channels. And that's what it looks like for the thermal optic phase modulators. So I'm not sure if I have any more plots beyond this one. I think that was the last one. So the key here is we don't have the pixel resolution that the Menlo flatteners do. So you see the Menlo flatteners have a perfectly flat spectrum. We have probably better dynamic range. It worked the first time we tried it, and it cost us $50K to do the whole thing, the design, fabrication, packaging, and the rest is just labor and testing. We got 4 of them, so the cost is $12,500 per unit, by the way. Now, the thing is, because we only have 20 channels in this first device, and we got a paper out on channel scaling and stuff like that. The trick here is that if you have high spatial frequency features, especially around the pump, which is pretty typical of LFC spectra, you may struggle to flatten that with a device like this, but if you're okay to not have a perfectly flat spectrum, but still do something, this could be helpful. Again, if you have the money and you're not constrained by space, the question is why go to photonics? If you're trying to do something like Francesco said today about putting something on a spacecraft, you're going to need to think about photonics. So anyway, this can do more than flattening. You can do spectral shaping, you can do all sorts of things. And we can certainly play with channel scaling and even move to other material platforms. So, I hope this sort of, whets your appetite to discuss other potential applications of these sorts of things. Thanks.
Thanks, Tim. Very interesting. Questions?
It was a little bit quick for me. What is the price? Okay, to get 4 fabricated 50. Okay, but okay, for the spacecraft, it could be interesting.
We actually have a 2nd generation device we haven't characterized yet that has a lot more channels than this. And what it does is it has the 20 nanometer wide channels on the edges, and around the pump region, we have much higher density channels. I can't remember how many total we have, but the idea there is that if you really want to flatten around some high frequency features, you could play with that. And then you could make an adaptable circuit. If you know what your spectrum is, you could order the right device for that. So yeah, there is that flexibility.
All right, I think in the interest of time, we'll have to move on, but let's thank them again. And our last group for the day is Team NIST. Scott, I actually don't know who's. Oh, okay. Pooja, are you online? Can you hear us?
Yeah.
Oh, great. Do you want to
yeah.
just share your screen and take it away?
Sure.
All right, we can see it.
Can you see it okay?
Yep, all good. Go ahead.
Okay, thank you, sir. Hi, I'm Pooja Shekhar, a graduate student in Rotterdam's group at CU Boulder. I'm going to outline our recent developments on developing a robust laser frequency combs for astronomy in the near infrared and blue optical. Astrocombs are one of the best calibration tools for EPRV, but not yet ideal. Our group's efforts to enhance its performance include developing an astrocomb that is simpler, more robust, and cost-effective, and achieve a better flatness for the spectral response of the laser frequency comb in the wavelength range of interest, and also extend the wavelength coverage of our astrocombs to the blue, that is like less than 500 nanometers in wavelength. Our electro-optic comb, which has been installed at the HPF spectrograph, has the advantage of simplicity and robustness. So in this talk, we are trying to address 2 main questions as to whether we can reduce the complexity and cost of these astrocomb technologies, and what is the efficient way to generate blue wavelengths from our near infrared comb. Finally, I'll briefly talk about the broadband noise, which is inherently present in all these higher rate combs, and why it is important to mitigate it. So our 30 GHz comb installed at HPF was a success. It is based on robust electro-optic modulation technologies and efficient supercontinuum generation using nanophotonic waveguides. It has been running continuously at a remote site for about 5 years with an uptime of approximately 98%. So how can we improve it further? One of the issues that we have found with this 30 gigahertz EO comb, even though it hasn't actually affected the final supercontinuum, is that the bandwidth of the initial EO comb is decreasing. This is due to the degradation of the high power RF amplifiers, which has been working throughout these 5 years with greater than 5 watts. And here we are trying to address this with a new resonant electro-optic design that requires much lower RF power to generate the same bandwidth comb. The second major upgrade that we are trying to implement is to pump at 1550 nanometers instead of 1 micron pump wavelength. This will benefit from the robust and mature telecom fiber technology and will enable a fiber integrated design that is more compact, low loss, and in turn might require low maintenance. Next thing that we are trying to improve is the amplitude stability of the comb lines in the wavelength range of interest to account for the detector nonlinearities, and then find an efficient way to generate blue wavelengths from our near-infrared comb. In this regard, we studied a compact fiber-integrated resonant electro-optic comb generator as shown in this schematic. It consists of a lithium niobate phase modulator inside a fabric cavity. The main advantage of this kind of a resonant electro-optic modulator instead of a cascaded EOM approach is a 10 times lower microwave power requirement to generate the same bandwidth comb. Here, the comb generator is seeded by a CW laser at 1550 nanometers and is driven by a 1 watt signal at 20 gigahertz. The resulting electro-optic 20 gigahertz comb spans around 50 nanometers as shown by this blue trace. This resonant electro-optic comb generator is commercially available and is kept inside a metal housing as shown in this image. As a result, it is simpler, more compact, and less expensive as compared to the cascaded EOM approach. However, it comes with a drawback also. It has a large insertion loss of approximately 25 dB. And this will result in some critical issues with respect to the broadband noise, which we'll discuss towards the end of this talk. However, I'd like to point that there is a solution to this issue also, which has been pointed out by Lonker and his group at Harvard University. They have developed this resonant EO comb generator on a thin film lithium niobate platform and has improved the pump to comb efficiency by 2 orders of magnitude using coupled microresonators as shown in this layout. Here, I'll present the supercontinuum generation from this 1550 nanometer resonant electro-optic comb. Using an all-fiber integrated approach, we are able to generate 20 gigahertz supercontinuum in anomalous dispersion, highly nonlinear fibers, as shown by this blue, green, and red traces. On replacing this hybrid HNLF with a silicon nitride waveguide, we were able to obtain an octave spanning 10 gigahertz spectrum as shown by this purple trace. Here, the solid lines corresponds to the experimentally measured spectrum, and the dotted lines refer to the simulated spectrum, which shows very good agreement. One interesting thing to note for this purple trace is a smooth amplitude response over the 800 to 1300 nanometers, which is the wavelength range of interest for the HPF spectrograph. And this can be easily flattened to generate a spectrum which has very less amplitude fluctuations, since most of the intensity fluctuations occur around the pump wavelength, which is farther away from this target wavelength range. Also, this spectrum shows possibility for self-referencing, so we don't need an extra auxiliary comb to stabilize each of these comb lines. This in turn reduces the complexity of the whole system much better. The main difference that we have incorporated in this design as compared to our previous efforts is of all fiber integrated temporal compression. Here, the comb pulses are amplified and sent through normal dispersion highly nonlinear fiber for spectral broadening in the initial stage. And then the broadened pulses are sent through a PM1550, which is anomalous dispersion at the pump wavelength to compensate for this extra dispersion added. So this PM1550 replaces the diffraction grating so that the pulses don't have to go back to free space from this fiber. And this results in a more compact and a low loss system, which can be easily maintained. Here, the spectrograms of the pulse at different points across the fiber shows that using this all fiber approach, we are able to compress or compensate for this nonlinear spectral phase quite efficiently. And using this all fiber temporal compression approach, we were able to obtain ultra short pulses with 57 femtoseconds at 20 gigahertz repetition rate and about 50 femtoseconds at 10 gigahertz repetition rate as shown here. And these are also very good quality pulses because most of the nonlinear spectral phase or the satellite pulses is less than 5% in amplitude compared to the peak power. This temporal compression is critical for generating a broadband nonlinear supercontinuum for astrocombs. Next, we'll move on to generating a frequency comb in the blue region and our efforts leading to it. As we have learned from several talks in this conference, we need a very good calibration source in the blue to detect an Earth-like analog. But developing a laser frequency comb in this region, like less than 500 nanometers, is challenging because the UV light degrades the silica-based fibers, and also the silicon nitride waveguide that we have employed before does not efficiently produce blue light from our near-infrared comb. To overcome or to address these challenges, we explored a new nanophotonic waveguide material called lithium niobate. The main advantages of this material, lithium niobate, is like a very strong second-order nonlinearity, in addition to the third-order nonlinearity which is present in silicon nitride waveguides. Also, they have a wide transparency range from UV to about mid-IR. There is also a technique called polling, which is an ability of the lithium niobate waveguides through which you can improve the conversion efficiency of nonlinear processes like harmonic generation and some frequency generation, which actually generates this wavelength less than 500 nanometers. And this results in a 10 times improved efficiency over silica fibers in this wavelength range. Also, the multi-octave spanning spectrum that can be generated from this pipeline gives direct access to the carrier envelope offset frequency without a need for an auxiliary frequency comb for stabilization. This shows the design of our chirped periodically poled lithium niobate. The waveguide was designed by Sung Han, a postdoc in our group, and was fabricated by our collaborators at Caltech and JPL. This shows the cross-section of our waveguide, where the lithium niobate is deposited on a silica substrate and is air-clad on top. And the top view of this waveguide shows that the initial part of the waveguide is unpoled for initial spectral broadening, and then it shows the poled region where the period ranges from 12.5 microns to 2.5 microns. And on the side, we can see the microscope image of the 2.5 micron polling period present in this waveguide. Initial acid testing, we used a 100 megahertz erbium fiber comb. So the 100 femtosecond pulses from this erbium comb were sent to the lithium niobate waveguide using lensed fiber. And the resulting output spectrum is shown here, which is like a broadband continuous spectrum spanning several octaves. To check the coherence of our broadband spectrum, we measured the beat signals in between the harmonics at 620 nanometers, 400 nanometers, as well as 350 nanometers. And we were able to see beat signals with good signal to noise ratio of 30 dB or above, which shows that this supercontinuum generation process retains the coherence of the initial near infrared comb. Also, using this waveguide, we were able to obtain a very good conversion efficiency of approximately 25% from the pump wavelength at 1550 nanometers to wavelength region of 350 to 550 nanometers. Here, this slide shows the agreement between the experimentally observed supercontinuum spectra from the lithium niobate, as well as our simulation results. This shows quite good agreement at various pulse energies coupled into the waveguide, ranging from 6.4 picojoules to 8 to 9 picojoules. And we can see that we need approximately 90 picojoules to get this continuous spectrum spanning several octaves. If the pulse energy is lower, there is like gaps between the harmonics. This shows the preliminary results we got with our 10 gigahertz 50 femtosecond source that I demonstrated before. The important point to note here is like for the same average power, a 10 gigahertz comb has 100 times lower pulse energy as compared to the 100 megahertz comb. Combined with the large insertion loss for this waveguide of approximately like 10 dB, we could couple only like less than 30 picojoules onto the waveguide at the available average powers of approximately 3 watts. So here we can see that the harmonics are efficiently generated, but the spectrum is not yet fully filled in. This shows scope for further improvements in developing a new design that improves the conversion efficiency into this wavelength region, as well as to improve the coupling efficiency into the waveguide. Here in this slide, we focus on an alternating polling structure that significantly increases the power in the wavelength region from like 350 to 500 nanometers as shown in this plot. Here, using this new design, we were able to increase the power by approximately 4 to 8 orders of magnitude. The main difference between the two designs is like the initial unpolled region is replaced by a very short polling period of 1.5 microns, which enhances the spectral broadening in the initial generation of the supercontinuum generation process. Here, it is also to be noted that the coupled energy is only like 30 picojoules, which is considered in the simulations, which corresponds to about 300 milliwatt at 10 gigahertz or a 600 milliwatt at 20 gigahertz, which can be achieved with our current system, along with an improved coupled efficiency into the waveguide. And lastly, I'll briefly discuss about the broadband noise present in this 10 plus gigahertz combs and why it is necessary to like mitigate it. The recent technologies like electro-optic combs and microcombs that have been widely used for generating this high repetition rate combs give rise to optical powers in the range of hundreds of microwatts or a few milliwatts. In order to generate a broadband spectrum, it is necessary to amplify these low output power signals to a few watts, which adds noise in between the comb lines. And this noise gets even further amplified during the process of supercontinuum generation, which we need for generating an astrocomb. So after several of our works on understanding this noise, it was found that it is necessary to add an extra high finesse filter cavity before the supercontinuum generation process in order to avoid the washing of comb lines at wavelengths away from the pump. So what does this filter cavity do is that it reduces the relative input intensity noise by approximately 16 dB as shown from this blue curve without the filter cavity to the red curve, which is with the filter cavity. This enhances the signal to noise ratio of the comb lines across the supercontinuum as shown by this curve. And this enables us to actually measure the carrier envelope offset frequency of our broadband 10 gigahertz comb. This coherence degradation in the presence of excess noise can be actually modeled by using a noisy 10 gigahertz pulse train as input to our simulations. So this is constructed by having a 10 gigahertz pulse train with random noise added in the form of short noise and amplitude spontaneous emission that we measured experimentally. And this is given as input to our silicon nitride in simulations. And the small video shows how the noise between the comb lines grow during this process of supercontinuum generation. The blue curve corresponds to the case where there is excess intensity noise at the input, that is without an added extra filter cavity. And the red curve corresponds to the case where there is an extra filter cavity that suppresses the input intensity noise. So the snippet shows that without the filter cavity, the simulation predicts approximately the same thing that we observed experimentally, that the comb lines around the 772 nanometers are almost washed out, while with the filter cavity, we can retain the coherence of our broadband frequency comb. We also tried measuring this wavelength-dependent relative intensity noise experimentally and compared it with our simulation results. And the experimental results are given by this red markers as shown on this right-hand side plot. And the simulation results are given by this blue trace, and its average is given by this white trace. And both of them show good agreement, which validates that our noise model actually predicts how the noise intensity noise grows during the supercontinuum generation process. In summary, we propose a resonant electro-optic frequency comb at 1515 nanometers, which can be made into a more compact fiber integrated design and has shown good broadband supercontinuum generation, which is possible using silicon nitride waveguide. And next, using the lithium niobate waveguide, we have shown that it is possible to generate a broadband frequency comb ranging from UV approximately like 350 to 2 microns using this lithium niobate waveguides. And we are still trying to address the challenges associated with this high repetition rate combs to generate this continuous broadband source in this wavelength range of interest from 350 to 550 nanometers. And also we looked at an important factor which is to be considered, that is the broadband noise between the comb lines and how we can efficiently understand and mitigate it. Thank you.
Very much, Pooja. Very interesting stuff. All of Team Boulder. Questions in the room? I know we're way over, so appreciate you all sticking around. Questions? Oh, I have one. So Pooja and co, how far away are we from a fully packaged lithium niobate based electro-optic astrocomb?
Yeah, it's still under, the work is still under progress. As we can see, we don't have this full broadband coverage yet with this high repetition rate combs. We are hoping that Sunghan, our postdoc, has started lithium niobate fabrication at NIST with improved like coupling efficiency, as well as like with this new design of pooling. We hope that we'll be able to cover this broadband coverage pretty soon. Yeah.
Very exciting nonetheless. So the next EPRV then is what I heard.
Hopefully,
right,
yeah.
Let's thank Pooja again and all the speakers for the week.
Thank you.
All right, we're already way over, but I encourage everyone to head to the poster hall and get some coffee. Thank you all for coming.